Our final topic with this slide set is mechanically stabilized earth walls, or MSE walls. And this is an interesting type of wall which has gained a lot of currency in construction, both transportation and elsewhere. And the concepts for designing it are the same. All retaining walls pretty much, in terms of their external stability, have pretty much the same principles. What changes is the implementation of those principles. And we're going to see that versus what we just went through with concrete gravity walls with MSE walls. But before we get into all that, I want to make a note about where this material is coming from. Up until this point in the course, most all the material I've presented has come from one or both books, mostly the Soils and Foundations reference manual, but some from Vroid as well. And I said in the beginning that there would be points in the course where I would depart from the books. And this is one of them. This topic and the next one, sheet piling walls, are where we're going to depart from the book. And part of that is due to the fact, I think whenever the feds get around to overhauling the Soils and Foundations reference manual, which they have not done since 2006, they will add a section on the design of MSE walls. They have become much more important in transportation, and they're also important elsewhere. So I think they will eventually get around to it. In the meanwhile, we have and I've also found there are also other federal publications. There are many textbooks that have a great deal of information on the design of these walls. I think from my standpoint, I have not found a really good approach to the design of these walls in any book, the feds or anywhere else, with one exception, which I'll show you, but I'm not sure it's as comprehensive as I would like it. And I don't believe in making people run around and buy and look up stuff just for one topic. So I've tried to condense everything into what we need for this course into these slides. So from here, for this, the slides. That's one reason why I continue to offer the slides separately, is because they are in parts of the course, your textbook, and this is one of them. MSE walls. Another thing about this is the slides. Now, when I've done, and those of you who actually sidetracked yourselves to see some of my soil mechanics videos, actually did a voiceover on the PowerPoints with some of those, and you do get a better look at the slides. This is sort of a compromise I came up with to try to replicate to some degree the class experience with the slides and me and all that. The reason why I put these here is to allow me to point out stuff on the slides, which I did extensively the last time, for example, and to interact with them to some degree. But I don't expect you to read everything up here. What I put this up here for additionally is to make sure you know where I am in the presentation. And then the presentation is available separately, and you can follow along. I know there are lighting issues and stuff like that with these videos, and I struggle with that from the beginning. In fact, for example, the lighting on this monitor is all the way as far as low as it will go because of the way that this setup works. So, in any event, just follow along. If you need details and formulas, and sometimes I'll flash them up on the screen like I did with bearing capacity, you can refer to the slides when you're actually sitting down and trying to solve problems. So let's get started with MSE walls. A mechanically stabilized earth wall is a generic term that includes reinforced soil, which is a term used when multiple layers of inclusions act as reinforcements and soil is placed as fill. The MSE walls are made up, and this diagram is a good way of illustrating that. On the front is facing. Facing can be vertical. It can also be, you can also have non-vertical MSE wall facings. We're not going to deal with that in this course. You can definitely have that, and I highly, and that's obviously, you see those. But for this course, we're going to stick with vertical facings. And you have these horizontal strips coming back from the wall that reinforce it. And they reinforce it back to a point. Now, I'm going to come back to this topic. You'll notice in this diagram that you've got a nice rectangular mass of soil. And that mass of soil is referred to as the reinforced soil. That's the reinforced soil. Or reinforced backfill. All MSE walls are backfilled from the get-go. You do not have a situation like with concrete gravity walls or later with sheet pile walls where you have the option in some situations to use the existing soil. With MSE walls, you basically have to write your own ticket, so to speak, on the backfill. And that's an advantage. That ensures that you have a nice, free-draining, cohesionless backfill, which, as I explained before, is a key to success with any retaining wall. But with MSE walls, it's mandatory. And of course, if you're doing something like, say, building an overpass and you want to use MSE walls on both sides of the overpass, then you have to build it up anyway. So you might as well build it up with this type of soil, or in some cases, soil. Might as well go ahead and build it up that way. But coming back to where I was, this area where the reinforcement is put through the soil, I'll just explain how that happens in just a minute, is called the reinforced backfill. And that reinforced backfill essentially becomes part of the wall. In gravity walls, we had a situation where you had above the heel, the soil acted as part of the wall. Well, this is how we get this in MSE walls. Behind this reinforced backfill is called the retained backfill. The retained backfill is generally the soil which is directly behind it that actually pushes against the reinforced backfill this way, and that becomes important for when we talk about when we talk about overturning and sliding. That becomes very important. So you'll need to keep an eye on that. And under all this is the foundation soil, which is a soil on top of which the MSE wall is placed. Now that foundation soil can be very significant. It obviously influences, as is the case with gravity walls, the friction that you can get along the bottom of it to ensure that against sliding. It's also important because down here at the bottom they call a leveling pad, or what it amounts to is a continuous footing. At least usually it's a continuous footing to support whatever vertical loads are on this. And there are some vertical loads. Some vertical loads due to just the weight of it. Some vertical loads are due to whatever is on top of this is being pushed down. It's not too much because it's not really a solid wall, as we'll see in just a minute. Another issue there, of course, is, and you can do bearing capacity and settlement analysis, which we will not do for the purposes of this exercise, of this discussion. However, an interesting aside is this. A few years ago, the Georgia DOT redid the Rocky Face exit in Dalton. And they were faced with some fairly loose soils, which were actually on top of the usual weathered rock we have around here. And to solve that, and their calculations showed them that they had a settlement issue under this. And you would think as narrow as it is, bearing capacity to be number one mode of failure. And they probably looked at that too. But they had a settlement issue. To deal with that settlement issue, both here and also the weight of this thing on top of the soil here is what both here and under here. To deal with the settlement issue, what they did was they drove a pile that used something very unusual in this geology, which is a pile compacted soil. They actually drove several thousand wood piles into the ground, basically, and we'll talk about cavity expansion when we get to driven piles. As you drive a pile on the ground, it displaces the soil that it's driven into, and that essentially expands. Well, if you've got a granular medium or any kind of particularly granular medium, and you do that, then the granular medium is going to compact just by volume. And we talked about volume considerations last time I mentioned them, and therefore that's one way of compacting soil, is by actually driving enough material in the ground so that the rest of it has to push against itself together, and that's how they compacted it. So settlement was definitely an issue, because not only is the MSE wall supporting itself, but it's supporting whatever's on top of it, which in that case was were off ramps and other roadways along the interstate. So in any event, that's an interesting sort of side note. So we also talk about in these definitions about geosynthetics. We are going to concentrate here on geosynthetics as the reinforcement for MSE walls. Originally, when MSE walls were first developed, most of the reinforcement was steel. Either steel strips or what I would kind of call a chicken wire kind of thing, where you've got very loose mesh. And chicken wire. But I think geosynthetics have pretty much taken, have become the dominant form of reinforcement. And we're going to concentrate on those. And I've mentioned these three regions. You need to make sure you fully understand which is which, because if you don't, you run the risk of assigning the wrong soil properties to the wrong region. And if you do that, then you can get into trouble. We'll see this when we get to the example. Applications, of course, retaining wall, whoop-de-doo. As you say up here, they can be used to replace gravity walls. Marine, I don't see that many marine applications. The biggest problem for using an MSE wall in a marine application is, it drains well. You don't have, tidal effects are not that bad. The biggest problem is going to be working in the wet. And you'll see that when we install them. You also have them for bridge approaches, interchanges like we talked about in Dalton, abutments and that sort of thing. They're very useful for where you need a very tall wall, and you can basically have to build the whole thing up. So they can be very high. Advantages. They're simple, they're easy to construct, they can be done with regular construction equipment. They don't require experienced craftsmen. That's especially important now, and I guess it's time, a little soapbox time. Our culture and our universities have certainly encouraged this, have basically told people that if you want to amount to anything in life, you have to go to university. And I know that some of you, particularly in an institution like ours, where we still have a fairly large number of non-traditional students that many of you have said, well, I'm tired of working this way, I want to move up. And that's good. And I also know that many of you labor under present and future debt to get this education. That's one reason why I feel a very strong responsibility to give it my best shot when I get up here. However, there are many places where people that, if they don't necessarily need to have any university education, the least, or some type of technical training at the community college level, and now we live in a state where we have that for free for many people, and they can, if they can go out and get work, their contribution, and if you've done this for work, your contribution is important. Because without good, skilled people, and modern construction requires a higher level of skill, even amongst just the people who, just the regular construction workers, require a higher level of skill and sophistication now than we did in the past. Because we don't have a lot of just the brute manual labor. A lot of that is handled by people, particularly excavators, have done a lot to eliminate that. Their role is essential. And one of the problems we face in modern construction today in the United States is that we don't have a really good base or enough people who have the skills and the training and the experience to perform even some of the what we would think were the ordinary tasks in a construction. You're going to have to, when you're designing, you have to stop and think, if I design this thing, will they be able to find the people that know how to build it? If we had a greater emphasis on vocational training, that would have made our jobs as engineers a lot easier. But in many cases, we have a shortage of people doing this kind of work. It takes everybody on a construction site and involved in a project to make it work and to make it work properly. And we cannot, as engineers, we cannot afford just to sit up and say, well, we're going to let this happen. That's the end. We need to stop and think, what do we need? Well, I've gone on long enough about that. One of the advantages of MSE Walls is that it does not require a level of skill that is frequently lacking or difficult to find on construction sites in the United States today. Less site preparation. Basically, you write your own ticket with an MSE wall. Reduces right-of-way acquisition. One of the things that I've mentioned with retaining walls about the real estate issue, the right-of-way issue is an important one. Many times, in the past, when you had lots of right-of-way wasn't the issue, had more room to maneuver, so to speak. You had the possibility for nice slopes and whatnot. You see some of these big, older interchanges with these long slopes and whatnot. Well, a lot of that's the thing of the past, especially when you're rehabbing a road or redoing a road or an interchange or whatever, and all of a sudden you don't have the room. Or if you're in a downtown development, you're trying to build something next to it, retaining walls are frequently the only way we to go. Disadvantages. The biggest disadvantage is also its biggest advantage. MSE requires granular backfill. Sometimes that backfill can be difficult to obtain, and that can be a very difficult kind of thing. Both you makes you get good quality backfill, but if you can't find it easily, then you've got a problem. So that is a difficult. a serious difficulty. There are other difficulties which I'll leave to the slide. Many of these facings are familiar looking to you. Notice, particularly over here, that you have a panel. MSE walls are not solid walls. They're stacked panels that are usually fitted together with some type of interlocking system that they to keep them together. But they're not panels. There's no real bending resistance, global overall bending resistance in an MSE wall. There just isn't. You'll have local bending resistance where the reinforcement is, but that's only to the extent between the spacing of the reinforcement. There's really no good way of. There's no global bending resistance with an MSE. It's totally flexible. Construction is fairly straightforward. You start with at the bottom, and you put a row of these blocks down and you attach the reinforcement to it, and you lay it out going back. Then as you see here, you get the old earth moving equipment moving, and you put this nice granular backfill over on top of it, and you fill it up. You put another set of blocks, and you put some more backfill, and then you put another layer of reinforcement down, and then you just keep going up until you get to the top, and you're done. It's a fairly, it does not require a great deal of sophisticated equipment, and it doesn't require a lot of tall lifting or heavy lifting either. The pieces are all reasonably light, and they can be easily assembled. There are two things I talked about earlier: the steel strips and steel grids that were used. These are sometimes you still see these. The big disadvantage of steel strips and steel grids is their corrosion. They're more likely to corrode, and that's an issue, especially if you have water running through the backfill, or you have corrosive types of liquids flowing through, which hopefully you don't. But over time, they'll have a corrosion issue. Normally, they're not very substantial, so it doesn't take long to corrode through them if they get a serious corrosion problem started. On the other hand, geogrids and geotextiles they're different kinds. What I've mentioned here is they're probably newer kinds, and they're always coming up with new formulations. The big disadvantage of geogrids is twofold. One is creep. All plastic materials are subject to some kind of creep, where over time they will grow, so to speak, under tension. The other thing, but it's not an issue with MSE walls, is UV. You get some environmental due to the presence of water and interaction with this, and getting tears from the backfill, particularly if it's a very granular or gravel backfill. You run the risk of having tears in the geotextiles. The UV is usually one thing that usually is the Waterloo for many geogrids, and sometimes it's hard to predict just when they formulate it whether it's going to have long-term UV survival or not. In the case of an MSE wall, that's not an issue. You're basically, and when geotech we say we bury our mistakes. Well, in this case, that's exactly what you bury the geogrids. And when you bury the geogrids, you eliminate the UV issue. Maybe a little bit, but not much. And this shows you some steel reinforcement. And again, like any either in grids, sometimes they're strip grids, sometimes they're a continuous grid. Then you've got the straight up strips. But all of them are the same, whether they start from the wall they work your way backward into the reinforced backfill. With geogrid reinforcement, it's the same thing. It attaches to the wall and goes back. And it does so layer by layer by layer by layer. MSE backfill must be uniform. It must be free draining. And the uniformity of the backfill simplifies the design a little bit. Because you don't have the issue of layering. We will see in sheeting that is a major issue with sheet piling is layering, and it also can be an issue, although we kind of snuck around it while no one was looking, with MSE. We snuck around the issue of layering. You can have layered soles with gravity walls as well. MSE backfill needs to be good quality and needs to be uniform. And here's a little flow chart for the design of MSE walls, just a quick. And you might use this particularly if you in a design project you need a little guidance. This is going to be this is for the external stability part. This is same old, same old. We have sliding external stability. We have sliding stability basically is what happens when the retained backfill pushes against the reinforced block. In other words, you have this force, and the only resisting force you have is whatever you have here on the bottom. Whatever friction developed between the retained and the foundation. So you've got that balance of forces. With overturning, we normally assume that it pivots about its bearing pad here, and you've got the same problem, only now the retained backfill has a force this way, and it basically tries to overturn this block. And the only thing that's keeping this block in place is the weight of the reinforced backfill, which basically has a centroid in the middle of it, since we're going to assume that most of our reinforced backfills are rectangular. And we're going to see that that's not an obvious thing to say in just a minute. We have bearing capacity and settlement, I might add. And then we have a global stability issue, which we talked about with gravity walls. Same thing. The internal stability is a little trickier. We say that the reinforced backfill acts as a block. In order for that to be true, it has to be properly designed. We have to get around one of the nasty problems of retaining walls, and it's one we're going to see again in sheet piling. We could have seen it if we had gone with anchored concrete walls, but if we've gone through an anchorage system, we will see it with sheet pile walls. But this is the basic problem. In my lectures on basic earth pressure theory, I basically say that what earth pressure is all about is that you've got a mass of soil, a triangle. If we assume a planar failure surface, and let's just do that for the minute, it assumes this, and this surface has an angle of psi from the horizontal right here. And you've got, if we experience failure along this failure surface, if we get earth pressure failure, this massive soil and this wall are going for a ride, and it's not going to be a very pleasant one if we have failure. Therefore, what we need to do with any wall reinforcement, it doesn't matter if we're talking about the strips here, any anchorage systems, soil nailing, if we do it that way. Of course, soil is a little different, which we'll talk about. But any kind of rock anchorage or anything like that, we have to put the anchor long enough and far enough into the earth to get past any kind of failure surface. In other words, over here. And in MSE wall terminology, we have two lengths. In other words, these have a total length to them. We have this LR. LR is the distance for at any point along the wall from the facing back to this failure surface. And obviously down here at the very base, it's 0. And up here towards the top, it's larger, and it varies. And this is a nice triangle, and we can determine LR using right triangle for any elevation along here. We need to know obviously the height, and we need to know this angle, and that gives us a right triangle for every reinforcement strip. We can do LR. LE on the other hand is what keeps this, and LR is, we don't count that particular we just don't count that. It doesn't really help us. The purpose of the strip is to get us back into the resistance zone. And LE is the distance along from here, from this surface back to wherever we stop the reinforcement in order to have static equilibrium. You say static equilibrium for what? That's the key to MSE walls. If I have a strip along here, it is subject to whatever effective stress is acting on it from the top. And the nice thing about MSE walls is, generally speaking, you don't have water issues, you don't have non-uniform soil issues. So computing the effective stress at any elevation is pretty straightforward. So it should not be an issue. And basically that effective stress acts vertically on whatever reinforcement grid I have here. And when it does, it's going to try to, that friction, it's another Coulomb block type of friction. That friction will resist this reinforcement being pulled. And if there's, so what's pulling it? What's pulling it is the fact that earth pressure is acting along the facing. And basically what we do is we assume that the earth pressure acts in a region which is halfway from the reinforcement down to the one below it, and halfway to the one above it, or to the top of the soil, whichever comes first. In other words, the region, if you say this right here, the halfway above, halfway below, that's the region. So basically, every reinforcement is really in a tug of war. Between, on this side, you've got the facing trying to pull the reinforcement out. And this side over here in this LE, which we make long enough so that the friction between the two will resist it. And of course, we have a factor of safety. We have a multiply factor of safety in there to make sure that doesn't happen. The whole design of MSE walls, from the standpoint of is basically a tug of war with every reinforcement strip between this trying to pull, between the facing and the air pressure in the face trying to pull it out, and the LE, the friction acting on the LE, trying to keep it there. There are two main objects we have in this. First, make LE long enough so that there's enough friction to resist earth pressure. Two, make the reinforcement strong enough so that you don't start out with your reinforcement in one piece and end up with the reinforcement in two pieces, or basically tearing the reinforcement from the facing. You're trying to avoid both. Those are your two objects in MSE wall design. Now, one thing I'll notice in this particular diagram is that the you'll notice that the top diagram has a break. It comes up and then it breaks and goes straight up. Basically 0.3 times H1, which is the height up to this point here, which will vary again. We ran into this problem with gravity walls about unlevel backfill, like sloping backfills. This particular is for, as you'll notice here, is for inextensible reinforcements, more like steel, whereas the bottom one is for extensible reinforcements, more like geosynthetics. We're going to concentrate on these. The value of psi is given this formula, which is 45 plus phi over 2, where phi is the is the internal friction angle of the reinforced backfill. Not the retained backfill, not the foundation soil, the reinforced backfill. We're going to, we've talked about I've already talked about the mechanical integrity of the reinforcement. And I've talked about keeping the reinforcement long enough. And actually, this slide is more or less a repeat of what I just said about that. We'll also focus on sliding and overturning as well. Computation of LR. LR will vary with elevation. It is 0 at the base of the wall. It increases as shown upward depending upon the type of reinforcement. You may want to lay this out in CAD for exact values. The same problem you have. It's a lot easier to lay it out if you lay out a picture, where you lay out this and then you lay out this wall and then you lay out all your elevations, and then you get all that, and then you can measure these lengths exactly and live happily ever after. You can do it analytically. You can do it. You can do it, or you can do it, with CAD. I think a picture would be easier. Computation of LE is again is the result of the tug of war thing I just talked about. And so let's put some numbers to all this. The allowable tension pull on the geogrid based upon the frictional is given by this formula right here. Normally the interaction coefficient, the coverage ratio of the two, usually for our purposes, is unity. And then there have LE. Sigma prime V is the effective stress, and that effective stress will include any, you can directly add a uniform surcharge to it. If you get into situations where you've got line loads or whatnot, things get a little complicated with that. But for uniform surcharge, it's fairly easy to add all that. And then on the resisting that is this, is the TREQ, which is simply equal to the spacing of the geogrids. Now, I want to be careful about that. SV is actually, like I said, it's the sum of half the distance from a geogrid to the one above it, plus half the distance there to the one below it. If you have uniform spacing, those two are the same. If you don't have uniform spacing, and sometimes you don't, then you have to compute SV for every layer. It's going to be different. And then sigma prime H, which is the lateral pressure against there. If you do the units on both, you will end up with kilonewtons per meter of walls or kips per foot of wall. The earth pressure is the same, is supported by that grid we talked about. Keep in mind, however, that we break down that horizontal pressure into vertical pressure times the active earth pressure coefficients. And for our purposes, we're going to stick mostly with Rankine. Usually we use Rankine theory in this case. The pullout factor of safety, and we're talking about just pullout at this point. We're not talking about the mechanical, we'll get to the mechanical in just a second. We're talking about pullout is equal to the T10, which is the allowable pull based upon the frictional action. We're not talking about the mechanical, we're talking about the frictional. In other words, make an LE long enough to generate enough friction to resist the pullout on the other end over the REQ, which is the strength required by the application. In other words, what's driving this whole thing literally are the driving force is the force on the geogrid by the lateral pressures of the wall. Those are the facts. For the design to be valid, the geogrids, the LE has to be, you have to have enough frictional forces on one end to resist the pull force on the other times that factor of safety. And so we substitute all this, and we get this nice equation down here at the bottom where the right-hand side has to be greater than the left-hand side for a valid design. And I say less than, well, actually, the right-hand side has to be greater than. This has to be greater than the left-hand side for a valid design, greater than or equal to. And you'll see why the greater than or equal to is important in just a minute. For the structural integrity, once you've computed the steps in this, you first compute the geotech requirements, and then you size the geogrid. The mechanical factor of safety needs to be the T allowable, which depends upon the geogrid and a lot of other factors, which we'll see in just a second, over the required strength of the application. The allowable tension pull is T ultimate over RF, 1D, RF, CR, RF, CD. These are all different factors, and I describe these factors here. And, they will vary depending upon the type of wall you have and this sort of thing. For a design to be valid, the allowable has to be greater than or equal to the required pull times the factor of safety, mechanical factor of safety. The mechanical factor of safety here and the factor of safety for this one, the pullout factor of safety, are not necessarily the same for a problem. So keep that in mind. Just, one factor of safety. No, not necessarily. Not necessarily at all. These are some suggested factors of safety, which are nice to know. Some design criteria for MSE walls, which probably we won't spend too much time unless you get into a design project. Okay, we have a design example here. It's a urban highway, geogrid reinforcement we're going to use. Vertical spacing of the strips is 750 millimeters, and that's based on the selection of the wall configuration, which we won't go into. The first row is located 375 millimeters from the topmost panel, half of that. That's going to be important to us in just a minute. Design height, external loads, the total design height is 7.8 meters to the gutter grade. The panel height is 7.5 meters vertical. And we have a uniform traffic surcharge of 9.4 kPa. There are 3 soils. Obviously, first foundation soil, that's the soil under it, is 30 degrees. And we're not going to worry about the other 2. The reinforced backfill, the backfill inside the strips, has a phi of 34 degrees, a little gravel in there probably, and unit weight 18.8 kilonewtons per cubic meter. The delta is equal to 11. That's for the friction. And the Ka, I go ahead and compute it as 0.28. You can verify that that is true. The retained backfill, the backfill behind the reinforcement, has a phi of 30 degrees and it's the same unit weight, but the Rankine earth pressure coefficient is a little higher at 0.33. Okay, general factors of safety, sliding, and 1.5, and the ones important to us, most important to us, are internal stability, the pullout, and mechanical. In this case, are both the same at 1 and 0.5. And MSE wall to suit these parameters. The most detailed solution is the it's a spreadsheet. Let me just show you that spreadsheet really quick. It's for your download pleasure. You have the most important thing to do with any problem is to properly state it. If you don't state the problem properly, you will not get a correct answer no matter how hard you try to fix it. The distance from the top of the wall, that's a function of the geometry. And there are 2 points at which there are no reinforcement. 0 at the top and 7.8 at the bottom. And then the distance from the bottom of the wall is really kind of the reverse of that. The reason why I do this is because I use this to compute LR. And how I do that is the triangle thing that I mentioned earlier. In other words, the further up you go from the base of the wall, the larger LR becomes. As you can see, it goes from 0 at the bottom to 4.15 at the top surface. Okay. Then from there, the effective stress, no overburden, is simply gamma times the distance from the top down there, and gamma times that, and gamma times that, and gamma all the way down. And that's all that they express the overburden. By the way, I put all of my variables for the soils down here. The effective stress with overburden is simply taking this and adding the overburden or the uniform surcharge with it. Uniform surcharge, as you remember from soil mechanics, and I know some of you, for some reason, some of my students struggle with the issue, the whole of uniform surcharge, when in fact uniform surcharge is the simplest. It basically assumes that you have an infinite surcharge that goes infinite in all directions, in this case all but one. And then the effect of the uniform surcharge is uniform not only this way, but also this way. So that's the that's the effect of the uniform surcharge. You just add it. Notice up to this point, and then we have the active earth pressure at every level. Notice that, and the active is simply this times Ka. Up to this point, I haven't done, all I've done is taken the properties and I've outlined it in different directions. That's all I've done. I haven't done anything else. And then, once I start doing that, let's see. Let's make sure I'm having a little bit of a let's see. There we go. Now we can do it that way. I'm having a little, and the left hand, you remember the formula that I put up at one point? The left hand side and the right hand side. The way I do it on the spreadsheet is I compute my left hand side and I compute my right hand side without LE, and then I divide the left-hand side by the right-hand side coefficient, and I get, voila, I get LE. And then I add that to LR, and I get the total length of the total length of the reinforcement at every level. Now I'm going to stop myself here, and I'm going to make a note. You will note that as a couple of things about this problem. One of them is LE is the same. Every level it's the same. You say, well, that's strange. Well, it is kind of funky in some ways. The reason why it is simple. As actually, it'll be easier to see when I do take the shortcut. So I'll just save that, but just for the it's the same. But the thing about it is that the total length decreases. Now you ask, that's not very good. That creates a very odd shape where basically if I were to literally replicate that on the back side of the wall, what I would have is instead of a nice, you noticed earlier my drawing showed a rectangular cross section for the reinforced backfill, it would have sort of it would have an angle on the back side. So you say, well, how do you get a rectangle when you got this? Well, the easiest way to solve that problem is basically to make them all and to assume that you're going to just go ahead and square the thing up, so to speak. In other words, make it purely rectangular, and the longest reinforcement strip is in fact the shape of it. It is the distance this way, and be done with it. I said, you remember that I said that the left-hand side, the right-hand side has to be greater than or equal to the left-hand side. LA can be longer. That's the other side. There are situations where this type of rectangle, that's kind of slope backside, makes sense. In most cases, however, I don't see this happening, because if you do it that way, I mean, if you've got some kind of soil on the backside or rock on the backside that makes that, then that makes sense. It does, for our purposes, it complicates the calculations. And also, in many cases, for example, if you're doing an overpass with an MSE wall, chances are you're not going to accomplish anything by just stopping it in a state. You're going to want to continue. In fact, if you've got two facing MSE walls, it's very possible that the two strips will not only face each other, but you could actually lay one strip out from one side to the other. So there's not as many advantages in cutting back on reinforced backfill as you think there are. So with that in mind, we're going to assume that 4.77 is the largest, and so the width of the reinforced earth is that, and we'll do our calculations. And even at that, you'll notice that the factor of safety against overturning is less than unity, and I'm going to talk about how to fix that problem in just a minute. In addition to what we showed on the other side of the spreadsheet, now that we're back over here, I can show you some of the basic variables. You'll see the factors that I put in here for the mechanical strength of the geogrid. We can compare that. We can get a factor of safety for that, and the various earth pressure. So it's important in any problem, again, to properly define your base variables before you get into the problem. So this is an example of how to do it with the spreadsheet. We're going to I'm going to now kind of let's see, we're going to make a few notes on the spreadsheet solution, and then we're going to get into the simplified one. It's important to compute the elevation of each one, as I've said. Ka is the same for all levels because the reinforced backfill is uniform, which it should be. It's also important to compute the LR, and LE is the same as no. We will see why. We're going to talk about a simplified computation of LE, and whether you can do this or not depends entirely upon the nature of the problem. It can be simplified the problem, you know, where LE is, you notice that LE was the same. There are good reasons for that. If you have uniform spacing at the reinforcement levels, the distance from the top reinforcement level to the surface of the soil is half the spacing. In other words, there's two ways of really looking at the spacing. One of them is the panel spacing, and the other one is the geogrid spacing, which are related to each other. If the panel spacing, generally, you know, we can, you know, as an average, that the panels are going to, you know, if the geogrid spacing, say, is 750 millimeters, we can pretty much assume that the panel spacing will be 375 on one side, on the other, the average. That's, I mean, that the geogrid connection to the panel is going to be in the middle. That's not necessarily absolutely the case, but we're going to assume, we're going to just talk that way. It may not, but in any event, that basically the geogrid spacing can either be conceived of as the spacing between one geogrid and the next, or it can be between the top of the zone and the bottom. And they're not unrelated, but in the case of uniform spacing, they're all the same. Everything is the same. The distance from the bottom reinforced label is base of the wall is half the spacing. And you'll note there's a little difference on the spreadsheet, and that's because of the, there's a little non-uniform in the bottom. We're not going to worry about that. The surcharge at the soil surface is uniform, and therefore it does not vary with depth. If you have a situation like with a line load where you've got varying, then you're faced with having to compute the effect of the line load for every level of it, for every different geogrid, and come up with an LE based on that. So therefore, if that happens, you substitute for the lateral earth pressure on the left-hand side, you get this. Note now that the vertical stresses on the left-hand side and the vertical stresses on the right-hand side cancel each other out. And with one single uniform spacing, that SV, I can solve for LE with an explicit equation. If I substitute I get 0.81 meters, which is virtually identical to the spreadsheet. And then L is equal to LR plus A, which will vary with depth. And again, it's, as I said, it's frequently better to make all the reinforcements the same to get a nice rectangular. Another thing you probably noticed about that with the length. You notice that the factor of safety while returning is fairly low. And you ask yourself, well, that's not good. No, it's not good. What it tells me is that there's not enough weight which has been in the reinforced backfill to balance the wall. To fix that problem, the easiest way to do it is to lengthen it. So therefore you would lengthen the strips further back to include more soil and therefore increase the resistance of it both to sliding, because you'll have more weight pushing down and more foundation area, and to overturning, you'll have more weight to resist being overturned by the retained backfill. So therefore, that's how you say. And this is an interesting case because in this particular case, the MSE Walls design, once you get past the technical, you know, getting the reinforcements basically to hold everything together, then what happens is that your design is driven more by the requirements to keep overturning from taking place than it is to keep the geogrid strips from either failing, either from pullout or from mechanical breakage. In other words, once you solve those two problems, then you have to make it longer to fix it. And it will not affect it may not, in this case, it will not affect the strength of the geogrid because the driving force doesn't change by making the reinforced backfill deeper. Now, there are certain situations where it depends if it affects the retained backfill in a certain way, it could. But again, strictly speaking, it will not. What you do as far as structural integrity is to pick, is to basically lay out a reinforcement scheme and then pick a geogrid that will not pull apart. That's the easiest way to do it. And if it does pull apart, you've got two options. One of them is to increase the strength of the geogrid. The other one is reduce the spacing. Those are your two basic options in MSE wall design. And you can go, and which one you pick depends on a lot of factors in terms of, because most MSE walls are kind of a package deal in terms of the way they're done, and so you have to look at what's available to you and balance those decisions. And of course, obviously the wider, the less the spacing, the more effort you're going to do to get the wall in. But this is the balance that you're trying to pick. The sliding forces are simply based on the friction, on the driving force of the retained backfill versus the friction of the bottom, what I mentioned before. Overturning forces are, as I've also mentioned before. And bearing capacity of settlement of the footing, and for that matter, the whole wall, is the same as a gravity wall. Most of the time, you get a wide enough retaining wall, you will not have much of a, your problems will not be with bearing capacity. At the footing, yes. The whole wall, you're not going to get, most of the time that'll be a settlement issue. This is a diagram I face, and so I know it's hard to read, but in any event, it's in your slides. For steel strips, the biggest difference between steel strips and geogrids is the fact that, generally speaking, a geogrid can be continuous. If you have a non-continuous geogrid, or you have a non-continuous, or you have any kind of major discontinuity between the two, let's put it that way. If your strips butt up, if you've got these, for example, like a grid strip, whether it be steel or geogrid, and you stop one, and the next one starts right next to it, you've got a continuous. If you don't, then you've got a situation where, and this shows that instead of a strip of resistance it has to do a block of resistance based upon not only the vertical spacing of the strips, but also the horizontal spacing of the strips. Our problems in this course will be focused on continuous types of reinforcement. And there are obviously advantages of doing that from a mechanical standpoint, in addition to making it easier to computation. But if you do run a situation where you've got strips that lay out, then you've got to consider the fact that there's a gap between those strips, and that gap needs to be accounted for not only by considering the horizontal resistance, or the depth of the horizontal, but also the width of the vertical resistance for each strip. A couple of other walls we're going to talk, just briefly mention, is gabion walls. Gabion walls are basically rocks put in chicken wire boxes and stacked up. They're very economical. They usually are, you see, they're surprisingly, you still see quite a few of them. They're not difficult to put in place and whatnot. You just stack them up. They're basically a form of gravity wall. If you don't have issues with drainage, in other words, if you don't care if you get some weepage out of the gabion, one thing, they're permeable. You will not get unbalanced hydrostatic forces with them because they'll just drain right out. If that's not an issue, gabion walls can be very useful in some situations. The other thing I want to just mention briefly are soil nailing and its close cousin rock nailing. Soil nailing basically is the concept is the same as the MSE wall, but the reinforcement is different. Instead of using these Geogrids strips, they will use generally grouted rods, which are basically hold the wall in place. The idea again is to have a mass of soil help to reinforce the wall into position. And that's pretty much, it's the same concept as MSE walls, but the implementation is very different. It's much better when you've got more competent soils, or you're not able to remove the soils. In other words, it's uneconomical to remove. You can remove anything, it doesn't matter how much money you want to spend. If it's uneconomical to remove them, then you can use soil nailing as an option. With the soil nail walls, I will warn you though, you need to consider your drainage. And that's also true with rock nailing as well, especially if you're in an area like ours where you have a great deal of artesian water. So that pretty much concludes this portion of the course relative to the first two types of walls we've considered, which are concrete gravity walls and MSE walls. So, as always, thanks for watching, and God bless.